video, we found an equation which basically replaced our previous equation, which we had found for, we had written for the first law of thermodynamics for the process between 1 and 3 as a whole. But now we have considered point 2. And with the knowledge of point 2, now we can write a different equation. And now I want to see how I can put different values, different points for point 2. How do I solve this equation? How do I solve this equation? The way to solve it is very simple. You see, point 2 Point 2 is somewhere between 80 degrees C and 20 degrees C. I assumed it not to be outside. I mean, I assume that we are not heating the cylinder first and then cooling it. But I assume that it's between 80 degrees C and 20 degrees C. So point 2 is certainly on 500 kilopascal line. That's one property. And if we decide on the other property, which is temperature, we would have all properties for point 2. So what I did was simply go to the tables and consider what happens if point 2 takes any of these values between 80 degrees C and 20 degrees C on the 500 kilopascal line. The answer was here, and please note very, very carefully. You see, what I did was that, well, I went to the 500 kilopascal line on the superheat table for R134A and just read values for 20 degrees C, 30, 40, up to 80 degrees C. This means that I have selected the line to be 500 kilopascal, and then I have selected different points on this line, and I have read all values for V, specific volume, U, and H for these points. And point 2 has to be among one of them. Okay, I say if we don't decide to do anything unusual and say heat it between these 2 points and then cool it and so on. But if we just lose mass and lose energy and heat transfer out of the cylinder piston device, then our point 2 would be among between 80 degrees C and 20 degrees C. Now, if it is on this line, line 2, 3, it has any of these values, its specific volume U and H are known. And that's very interesting because you have the volume, you have the specific volume for point 2, so you have the mass of point 2. And that is the mass of point 2. You see, we have volumes V1 equals V2, and that equals V1 times M1, and we have all the values, and that equals V1, which was 0.0322659 times M1, which was 2 kilograms, and therefore V1 would equal 0.065 cubic meters, and V3 would equal, it was 1 kilogram times its specific volume, which was 0.04215, and therefore V3 was 0.042115 cubic meters. So once we have V2, if we have a specific volume, we could decide how much mass there is into it. And that's exactly what we have done. If we know a specific volume at point 2, if it is assume that 2 is at 20 degrees C or anything here. If we know a specific volume, we would know the mass, M2. And therefore, if we know the mass, we know how much mass has left. This column tells us for any of these temperature, what's the mass at point 2 and how much mass has left. Our control volume between points 1 and 2 is basically 2 minus this value. It is 2 minus this any of these values. HE12 is the average between H1 and the values in this column. So HE12 is possible to calculate, and therefore once we have all these values, we could insert them into this equation, and calculate OQ12. Now, if we know how much mass has left between 1, 2, the rest of it should leave between 2 and 3. I mean, it was 2 kilograms, um, um, 1.551 was left at point 2, and at point 3 it would be 1. So 0.551 kilogram should leave between 2 and 3. And the same, so the mass leaving between points 2 and 3 are listed here. HE23, which we need it for here, for this value, was between H2 and H3. It is the average between H2 and H3. H3 we knew it before, and H2 is in this column. So we just add them, divide them by 2, and it would be this column. Inserting into this equation with the knowledge of W23 to be minus 11.6, the outcome for this equation would be Q23, which varies for different temperatures, for different intermediate temperatures. So in fact, what we can do is just for any temperature, for any intermediate temperature, for any point 2, for any temperature for point 2, we can calculate Q12 and Q23. If you have Q12 and you have Q23, we can add them together and get Q12 plus Q23, which is these two terms added together, and I have done it here for different values. And here, what I have done is that I have just calculated this term. I mean, I had Me12 times He12 and Me23 times He23. I have multiplied them, add them together, and this would be an average, uh, in fact, mass-weighted average for He. Compare this with the value that we had before. It was 290.2. For 290.2 was an average that we assumed, and with this average, we managed to calculate Q to be 60.7. Now we have found a new way of averaging. It is a mass-weighted averaging, and we see that with this way of averaging, Q12 plus Q23 would be 74.5. 5 to 36.5. Now let's sum up what all this is telling us. You see, to start with, I just wrote the first law of thermodynamics and tried to do some very simple averaging for HE and calculated Q from it. Okay, and the value was is 60.7 kilojoules. Then I said, well, there are two processes. I'm just taking an simplified average between the two would not do. So I wrote our equations for the two processes and add them together. And now I have a new way of finding an average. MEHE is not just simple 1 kilogram times 1 kilogram that had left the control volume times an average between initial and final entropy. But I found a better way of um, making that, finding that average, and that average is this value, is a mass-weighted average. So for every mass that leaves our control volume, I have assumed an average which is more appropriate for it. And now I have calculated Q and found different values. So the previous MEHEE, which we had, which was 290, was somewhere in between. And the Q we calculate, 60.7, was somewhere around here. Now we have a lot of different possibilities. How could all these temperatures happen? How could all these mass flows happen? I mean, what have we changed in this table? What do different rows in this table represent? And the question is very clear here in this figure. You see, there's a balance between what is the mass that you let out, how much you open the valve, and how much heat transfer happens from the cylinder. Now, this balance could change point two, and all alternatives are there. You see, these are the alternatives that I am suggesting. I say this, that if M2 is 1.551, I mean, if 0.449 kilograms leaves during 1-2, and the Q12 is minus 47.5, what happens? It happens that the temperature at point 2 would be 20. If the mass leaving is 0.594, which is more, it means that you have opened the valve more, then the heat transfer would be less, would be 38.2, and the temperature would be 40 degrees C. So these are different possibilities when how much we open the valve and increase the mass flow rate, or how much more heat transfer we have. Of course, here we have to add heat to the cylinder to keep it at these 2 points, which is perhaps what we won't want. So if there is no heat transfer, at point between for the process 1, 2, no heat transfer for the process 1, 2, I would write this here. No heat transfer if no heat transfer at 1, 2, then you see that the Q should be somewhere around here, and I have calculated to be at temperature T equals 63.7 degrees C. So If there is no heat transfer, the temperature would be somewhere between 60 and 70, and that would be 63.7. There's also the case that there could be no heat transfer between 2 and 3. I mean, all heat transfer happens if the temperature is reduced to 20 degrees, which is final temperature at point 2. Therefore, all heat transfer has happened during 1, 2, and therefore there is no heat transfer between 2 and 3. So there is a balance, in fact, in this problem between how open the valve is and how much heat transfer happens during each of these two processes. And with this balance, it's possible to have different heat transfers, and the sum of mass transfer would be one anyway. I mean, the sum of these two, in any line, the sum of these two columns would be 1 at 0.798 to 0.202, and that would be 1. And that's the same for any row. So the total mass leaving the control volume is 1, of course. But it's very important how much of it leaves our control volume during 1, 2, and how much of it leaves our control volume in 2, 3. And that changed the whole picture. Please note that for a different balance between the mass flow rate and heat transfer between processes 1, 2, and 2, 3, the average, the real average, the better average for HE would change, and therefore the heat transfer would change. The change is not negligible. In fact, it's very important. You see, it's about 40 kilojoules change. And in a 60 kilojoule, I mean, my previous calculation gave us a 60 kilojoule heat transfer. And now you see that for a better assumption and for a different balance of heat transfer between the two processes, the answer could change anywhere between 36.5 and 74.5, which is almost 50% up and down between what we had calculated before. And this is the correct answer. This is the correct solution where we consider point 2 in the middle, and we consider the balance between the mass leaving the control volume uh, and also the heat transfer from the control volume. Well, thanks very much for watching, and cheers.